So let's have a look at combining waves, and that's what this is all about. Taking a couple of waves, a sine omega t plus b cos omega t, and combine them into one wave. And we've seen waves a bit like this. Y equals that sort of wave. R would be what to do with the wave? What would R represent? We've talked about before. If I plotted a wave, the amplitude of the wave, right. So there's an example of one here. I plotted that y equals a sine omega x plus alpha. So a is the amplitude of the wave. And so r is the amplitude of the wave. Omega stands for the, to do with the frequency, the angular velocity, which is 2 pi times the frequency. Do you remember you can work out the frequency if you know the angular velocity in the formula. Omega equals 2 pi f. Omega equals 2 pi f. We can combine two waves with the same angular velocity. So this works if we've got the same angular velocity. Look, omega. They've both got the same angular velocity. We can combine those two waves into one wave. And if you look at it, you notice that this wave has got an amplitude which is different to these two. So that might have, this one might have amplitude B, this one might have amplitude A. And if we combine the waves, we end up with a combined wave with an amplitude that's different to those two. It might be the addition of the two. We'll find out. Okay. And we also note that when we combine the waves, it's got the same angular velocity as the other wave, but with this extra bit added. Can you remember what that bit represents? The phase angle. In other words, it's saying that the wave might not be starting at 0. So if we look at an example in an autograph, this example again, we can see I've typed in y equals a sine omega x plus alpha, as I say. By default, autograph sets a, w or omega, and alpha as 1. So I haven't changed any of those figures, so they're all 1. So if we look at it, we can see that the amplitude is 1 to start off. And we can see that omega, we could work out what omega was, because omega is 2 pi f. So if omega is 1, 1 divided by 2 pi will give me the frequency, and if I worked out what 1 divided by 2 pi was, to get the frequency, the period is 2 pi over 1, the inverse. So the period is in fact 2 pi. The time for one complete oscillation should be 2 pi. And so the distance from, I'm not sure I'm going to be able to do this with this. So if we look at this wave, putting it in the notes now, then that distance, the period, should be 2 pi. So, but that point is not at 2 pi. Why not? Because of the phase, yes. The distance from there to there is 2 pi. The whole thing's been shifted that way a bit, hasn't it? So if I add this extra distance here on, 1 in other words, and added this onto here, I would get 2 pi, 6 point something or other. So that's what this wave looks like. I can combine two waves to get one wave. Actually, often in engineering and science, we go the other way. We would take a wave, this sort of wave, and go this way, split it into its components of sine and cosine waves. And if you're interested in sound, and particularly digitalized sound, where you have something like a graphic equalizer that allows you to change the amplitudes of the bass or the middle frequencies or the high frequencies, what somebody's done in that wave is taken a complex wave, which will be something not unlike that, but it'll have lots of different components, and split it into its individual sines and cosine waves, so that you can then manipulate each one independently. And that's called Fourier analysis. So this idea of combining waves is sort of like a precursor to those things, which is why we're looking at it now. So what we're going to do is to work out how to calculate what this value is and this value is. Okay, given two waves, a sine omega t and b cos omega t, knowing these values, A, B, here, I need to work out what R and phi are in that combined wave, and that's what this is about.